Welcome to section 10.6, the vector product of two vectors. In a previous section, we looked at one way to multiply two vectors, where our answer was a single value, a scalar quantity. In this section, we're going to look at another way to multiply two vectors, where our answer is another vector. At the end of this section, we should be able to answer these questions. What is the other name for the vector product? What notation is used for the vector product? What does the vector product represent? What is one way to calculate the magnitude of the cross product? What is the right-hand rule? How do we compute the cross product? What are the cross products of the unit vectors? And what is the geometrical meaning of the magnitude of the cross product? Well, the other name for the vector product is the cross product of two vectors, and it's a vector with these properties. A cross B is perpendicular to the plane containing A and B. The magnitude of A cross B is equal to this computation. The magnitude of A times the magnitude of B times the sine of the angle between the two vectors, where the angle between the two vectors is created when they are placed tail to tail. Now the direction of this cross product is determined by what we call the right-hand rule. Here's how the right-hand rule will work. First, you put your fingers of your right hand so that they curl in the shortest direction from the first vector to the second vector in your cross product. So if I were doing A cross B, my hand would go along, my right hand would point in the direction of A so that I could curl my right hand, or that vector A, into vector B. The cross product is in the same direction that my thumb would point. So if you look at this diagram right here, you can see that I start by placing my right hand pointing in the direction of A so that I can curl around into B, which forces my thumb to point straight up in the direction of C. Another way to work the right-hand rule is to place your right hand so that your index finger lies along the first vector and your middle finger lies along the second vector. So if I'm doing V cross W in this diagram, my index finger goes along V and my middle finger goes along W. That forces my thumb to point up along the plane of the page, so that would be the direction of my cross product. I'm going to include a video that I found that shows this demonstration pretty well, I think. So watch that, and then we'll come back to my lecture.
Okay, so here you can see I have vector A and I have vector B. So if I want to figure out the direction of the cross product, A cross B, first I'm going to put my fingers in the direction of A, and then I'm going to curl them in the direction of B. And notice that when I do that, I can only do that with my right hand, of course, with my thumb pointing straight up. Okay? If I tried to do A cross B with my hand in any other orientation, it wouldn't work. I wouldn't be able to bend my fingers in the direction of B, having first placed them in the direction of A. So, therefore, for A cross B with these two vectors, the direction of the cross product will be straight out of the page. If we were to do B cross A, then first we'd put my fingers in the direction of B and try to bend them in the direction of A. Now I can't do that when my hand is in this orientation. I have to change the orientation of my hand. And when I do that, now my thumb is going to be pointing straight into the page. So if I do B cross A, the direction of B cross A is straight into the page with these two vectors. How do you deal with cross product when both of your vectors aren't in the plane of the page? Here I have examples where we have one vector that's in the plane of the page and one vector that is either pointing into the page or out of the page. So in my first case, if I want to do vector A cross vector B, Once again, I put my fingers in the direction of vector A, the first one, because it's A cross B. And then, since B is into the page, I have to rotate my hand around so that I can bend my fingers towards the direction of in the page. And when I do that, my thumb points in the direction of the top of the page. So the direction of A cross B is towards the top of the page. In my second example, I have A coming out of the page and B is going towards the top of the page. So once again, I put my fingers in the direction of A and notice that they are pointing straight up, and then I'm simply going to bend them in the same direction as B, which is towards the top of the page, and when I do that, my thumb points to the left. So in this case, the direction of A cross B is to the left.
Now that we've looked at how the right-hand rule works, let's apply it to our unit vectors along each of the axes and see what their cross products should be equal to. Now if we look at the cross product of I cross I, well, we know that the magnitude of I is 1 because it's a unit vector, but the angle between a vector and itself is 0, and the sign of 0 is 0. So the cross product of a vector with itself is going to be equal to 0. And that's true for all three of these cross products. Now, try and apply the right-hand rule to each of these other 6 situations to see how they will play out. I cross J, if you take your right hand, lay it along your I axis, and curl into your J axis, your thumb should be pointing up, which would mean that I cross J is equal to K. Now, J cross I, on the other hand, would mean that you'd have to rotate your hand 180 degrees so that now your thumb would be pointing down and you would get negative K. J cross K. So if K is straight up and you curled into your J vector, you should see that you end up with the I vector, which means that K cross J is going to go in the opposite direction. Now I cross K, try it again, should give you a negative J. Think about why that would happen. And K cross I then should give you a positive J. Now that we know how each of these cross products will work out for our unit vectors along the axes, we can determine a formula for the cross product of any 2 vectors. Just follow along and you'll see what ultimately our cross product calculation should be. So if we're doing A cross B, I've got these 2 vectors AI plus BJ plus CK and DI plus EJ plus FK. So I'm going to use the cross product. So what I'm going to do here is I'm going to do a FOIL calculation, or a superfoil, since there's 3 terms. Just follow along and you'll see how this works. So first I'll distribute the AI across the DI plus EJ plus FK. So AI times DI would be AD times I cross I. And then AE times I cross J plus AF times I cross K. We'll do the same thing with the BJ vector and cross product that with DI plus EJ plus FK, and we'll get BD times J cross I plus BE times J cross J plus BF times J cross K. And finally, we'll distribute the CK, and we'll get this row right here, CD times K cross I plus CE times K cross J plus CF times K cross K. Now, if you'll notice, right down that middle diagonal, we have an I cross I, a J cross J, and a K cross K, which we determined just now is equal to 0. So let's carry that over to another page. And I'm going to, if I remove each of these terms, because each of these cross products is 0, I'm left with this expression. Now I've rearranged it a little bit. I've got my J cross K from here, and my K cross J from here in my first row. And then I have my I cross K and my K cross I in the second row. And then I cross J and J cross I in the third row. But I've calculated what each one of these is earlier. J cross K is I, K cross J is negative I cross K is negative J, and K cross I is J. I cross J is K, and J cross I is negative K. So if I combine my I information, I see that I have BF minus CE I minus AF minus CD. I've reversed the order of these, and you'll see why later. Plus AE minus BD K. So that's what my cross product will be equal to, is this calculation. Now remembering that calculation can be a pain. So here's a way to organize your information so that you can get these values correct every time. What we're going to do is we're going to take a matrix approach. We're going to take the 3 unit vectors I, J, and K and place them in the top row of a 3 by 3 matrix. Then I will take the A components and place them in the second row. Here's A, B, and C. And finally in the third row, the B components. From that set of information, I'm going to create 3 smaller 2 by 2 matrices. And the way I'm going to create them is as so. For each of these 2 by 2 matrices is going to be a component in my cross product answer. To find the I component, what I'm going to do is I'm going to eliminate the rows associated with I, and then take those 4 values that are left, B, C, E, and F, and create my 2 by 2 matrix. Then I'm going to do the same thing to create my vector for J. I'm going to eliminate the row and column that J is associated with, and now I have A, C, D, F for J. And finally, I'm going to do the same thing to create my K matrix. Eliminate the row and column associated with K, and I end up with A, B, D, E. Now, if I take these matrices 2 by 2 and I calculate their determinant, which is the diagonal from left to right minus the diagonal from right to left. So first I multiply B times F, and then I subtract the right-left diagonal, so CE. And that gives me I. Now here, if I do that, I get AF minus CD for J. And finally, I get AE minus BD for K. Now, the only thing we have to remember is that there's actually a negative sign here for the AF minus CD calculation to match our cross product calculation that we did in the previous pages. Now, it's very important that we don't forget that negative sign in our final calculation from these matrices. So let's work out an example. Here we have A and B, 3i plus 5j plus 7k, and 11i plus 2j plus 13k. To find the cross product, first thing I'm going to do is create my 3 by 3 matrix to help me organize my information. So I, j, and k. And then my A coefficients, so 3, 5, 7. And B being 11, 2, and 13. So that's going to create my set of 2 by 2 matrices for I and j. Now remember that for j, there's a minus sign in front of the j matrix and a plus sign in front of the k matrix. So now I organize my information. So for I, if I eliminate the row and column for I get 5, 7, 2, and 13. For j, I get 3, 7, 11, and 13. And for k, I get 3, 5, 11, and 2. Now we calculate the determinants. So 5 times 13 is 65 minus 14 for I. So the diagonal going from left to right minus the diagonal from right to left. And then we have minus 3 times 13, or 39, minus 7 times 11, or 77. J plus 3 times 2, 6, minus 5 times 11, 55, k. And when we simplify, remembering that we have that minus on the j value, we end up with A cross B being 51i plus 38j minus 49k.